In this video, I want to tie together some of the ideas that we've been pulling out of translational motion and some of the ideas that we've been creating in rotational motion and try to smush them together in a way that will allow us to solve problems in somewhat different ways. Okay, so first of all, we have two concepts that we learned earlier. We have the position and displacement, which are given by, x and delta x. Let's just say delta x. And then we have the angular displacement corresponding to that, delta theta. So let's start with, how is the good old-fashioned displacement, delta x, related to the angular displacement, delta theta? So in order to determine that, I've drawn a little picture over on the right here with an object that has an initial state in red and a final state in blue. And in order to kind of analyze this motion, we would want to picture, an arm like this. Let's do a little bit thicker of a line, if I can do that. There's the line thickness. Okay. So we have an arm here, which gives the, angle and the position vector for the red guy. And then we have another arm coming from the center of the circle that goes to the blue guy. And what we mean when we say delta theta is this, the angle here between the red arm and the blue arm. And what we basically mean by delta x, now again, it's a little bit squirrely what we mean by delta x. The actual displacement vector here would be a vector that points directly from the red one to the blue one, irrespective of the fact that it's moving on a circle. But as in the example I did with the insect on the record, sometimes we actually have to break away from that a little bit and measure x just along the perimeter of the circle, which I'm going to do right now. So imagine that delta x actually in this case is the distance traveled along the perimeter of the circle. So it's actually a curve. It's actually the length of that arc from the red guy to the blue guy. In this case, what you'll notice is these three variables define an arc of a circle. Delta theta is the angle subtended by that arc, and delta x is the length of that arc. And then both of these sides of the arc, of course, are r, and this is also r because it's a circle. So all these arms have length r. So if you go back to kind of geometry 101 or whatever, you may or may not remember that the length of an arc is equal to the length of an arc, delta x, is equal to the angle subtended by the arc times the radius of the circle. So there's a very simple relationship between these two variables. Namely, it's just to multiply by r to go from one to the other. That turns out to be a very useful thing to remember. Now, we know that velocity on average was delta x over delta t. Well, it's also true, I don't know if I mentioned this yet, but it's also true that the same thing is true for angular velocity. Angular velocity is just delta theta over delta t in the same sense. V tells you how x is changing. Omega tells you how theta is changing. So because of that, since V average, basically, since V average is delta x over delta t, and omega average is delta theta over delta t, and it's the same delta t in both cases, if delta x equals r delta theta, that means also V equals r times omega. The exact same relationship holds between velocity and angular velocity as the relationship between displacement and angular displacement. And furthermore, over here, the average acceleration is delta v over delta t, and over here, the average alpha is going to be delta omega over delta t. So the same relationship here holds as well, but we have to be careful to apply it only to the tangential acceleration, because the centripetal acceleration has no influence on alpha whatsoever. But anyways, there's this very simple relationship between the linear variables and the rotational variables, that the linear variables are just r times the rotational variables. And because of that, you can actually use a lot of times the rotational variables in place of the linear variables, because that r is ultimately just going to cancel out between everything. For example, let's say kinematic equations is a great example. Let's say you have a kinematic equation like, let's just pick a simple one. Let's say you have a kinematic equation like VF equals VO plus AT. If we plug in these relationships here, so VF is R times omega F, and VO is R times omega O, and A is R times alpha, because by A there, we really just mean the tangential acceleration. All these factors of R cancel out, and we end up getting that the exact same equation holds for rotational variables as the equation for linear variables. And that's true for all 5 kinematic equations. If you make the substitution, replace X with theta, replace V with omega, and replace A with alpha, the kinematic equations still work. So you can apply the kinematic equations directly to the rotational variables, which is highly useful. So I'll illustrate that in a future video. In addition, these relationships here are often also useful for describing how the different variables are related to each other, which perhaps I'll show you an example of that as well. But this is the main concept.